Unit 5, Ionic Compounds. Chapter 1 has us looking at some of the how ions bond. Now, last unit, we talked a lot at great length on how covalent compounds bond, very little on their naming. For ionic compounds, this is almost quite the opposite. We talk very little about how they bond, mainly because of the amount of information and some of the things that we don't have access to that prevent us from really exploring how they bond a little bit more, but more on their naming. Since these compounds have a different type of naming scheme, we'll spend more time talking about that. Chapter 2 has a complete, that is all we talk about, is how ionic compounds are actually named. And then Chapter 3 has us looking at some other things. But for this unit, we're going to start the naming process, but we're going to start off talking about how they bond. Ionic bonds are ones that are held together by electrostatic forces, meaning the difference in charges, such as a cation and an anion, are holding them together. This is different than those that are held together by covalent compounds, which are sharing of electrons, if you remember. So ionic bonds are the making and taking of electrons. So someone's going to take, someone's going to lose. So there's always a mix and match of who's giving and who's taking of the electrons. Now these electrons that are being given and taken are the same ones that were being shared in the last unit, but these ones, they are still talking about the valence electrons in an atom, and they're the ones that are responsible for the giving and the taking. And we can see on our periodic table, kind of usually, and there's some trends on who gives and who takes. And we'll talk more about that, and it will start to connect some of the ideas that we've been talking about over the last couple of units. Ionic compounds are usually, for the most part, all of them solids at room temperature. There are a couple different types. There are two classes of them. There are crystalline, meaning they have a nice regular repeating structure, as we can see here on the screen, where we have our sodium and our chlorine ions present at each individual repeating corners. This is known as a nice cubic crystalline structure, as a crystalline solid. Amorphous, man, glass isn't really a good example of this, as it is more of a kind of, not really it's that, but amorphous means that there's no repeating pattern. And the reason why I use glass as an example as opposed to another compound is that when you break glass outside of a one that has been tempered, meaning one that's been changed, that you have, it does not break in a nice pattern. How it breaks is very irregular, and therefore does not have that nice repeating pattern. Now, glass that is in your car does have a pattern to it, and that is why it's a little bit different. It kind of gives it that cube look. It's done that way on purpose. And if you take a salt, it will cube. And you can think about this, how these break and some of those types of things. If you think back into where maybe when you took an earth science class, usually most classes, it's an 8th grade earth science class, is when you were looking at minerals and how the minerals broke. They talked about the cleavage in which they use, or how they broke, and how they're cubic and base and some of those types of different ways. So that's kind of where that comes from, is whether it is crystalline, it would have a nice repeating, or if it was amorphous and therefore it would not be repeating. It was very random in how it broke. At room temperature, most ionic compounds are. So the bonding that ionic is very strong, and that is because it requires, we know that it's strong because it requires a lot of energy for them to melt. It's usually commonly said that you will actually melt your cooking pot before you are able to actually melt any salt. That's one quick way of knowing if you made the mistake of putting sugar in your bowl or your pot for melting, as opposed to salt. The salt will take for a very long time. And if I'm not mistaken, very difficult to reach the temperatures that would require at a normal house. It would require very high amounts, and so it would be very difficult for us to even achieve those temperatures. One property that they do not conduct electricity in their solid form, but once you put that salt in a liquid, they dissociate or dissolve, and therefore then do allow for that difference in ions, those charges to take place, and that allows the electricity to pass. Now, metallics bond a little bit differently, and they kind of do things a little bit differently. Their valence electrons are just kind of loosely held around, and they have very low ionization energies. They tend to lose their electrons. That's what allows them to have electricity to pass through them. Is that kind of through that sea of electrons that we kind of look at? Is that the electrons are just kind of floating about, and the electrons are allowed to just pass from one to the other as the electricity is pushed in on one side of the wire, and that allows that to happen. This also allows for them to be reshaped and moved easily, and that's why they're malleable a lot of times, is that they're able to be reshaped and moved, and those electrons are able to just kind of pass and go wherever they need to go as long as they're hanging around one of the metals in that. Ionic compounds can conduct an electric current. Metals can also combine with other metals. Now, these are known as mixtures. They are mixtures. And it's like you need to understand that it is a mixture. Alloys are mixtures. Alloys are mixtures. They are not, by any stretch of the imagination, alloys are not a new compound, but instead are a mixture. Now, normally this would mean that they are a homogeneous mixture, because you can't really tell the difference between them or the separation of them, but they are a mixture. Alloys, usually, again, you're going to have two or more of them, and some of them have different percentages and will change the properties based on those percentages. Brass is an alloy of copper and zinc, and is found a lot of times in our plumbing fittings. The copper is very soft and needs to be hardened at certain junction points, and that's why adding a little bit of zinc to it allows for that to actually happen. It allows those points to be hardened and allow for threadings and things to be able to change, and for like pumps and changing of where those are at. And so those points are good to have brass fittings. Now, a bronze was kind of one where we had a whole era in history named after it, the Bronze Age. Well, the Bronze Age came based on the tools and the weaponry that was used during that time, and it was allowed that during copper and tin was put in a fire, and they kind of look at it and go, oh, look, it makes something that is harder than just copper. It gave kind of went from the Stone Age to the Bronze Age, and then after the Bronze Age, you now become to the Iron Age, and where iron is even stronger. And how they deal with iron is they learn some other things, that if they put iron in the fire and add a little bit of carbon to it, you can start to become and getting some steel properties and make it even harder. And that is where you kind of get the steel industries coming from. And now a lot of times, most of the steel that we have is actually already been mined and manufactured, and a lot of times it's just recycled. And so all these little alloys are very new, and there's a lot of very interesting chemistry that happens from one to the other as we look at different alloys. A lot of the alloys that are used in computers, some of these alloys are used in the space industry, and a lot of them are used in our own phones as they are imprinted in small amounts. The valence electrons of metals can be modeled as alloys are important because they Now we're going to talk about naming. What we've already done with bonding. Yeah, for the most part, that's really all we need for our bonding, and to understand that those items are found in our everyday life is important. How they are actually structurally done, I think we could take a little bit further look at, but I think for this class on how it works, I think it's very, it works for us, and it does what we need it to do. It serves its purpose. Naming the compounds is extremely important. That is based on some rules set forth by the IUPAC. Now, it is important that you learn the rules. I cannot agree more with the textbook, with whoever says it. Now, there will be some things that I will do that are technically against the rules, and that is for the main reason why I do this, is so that you learn how to see and it becomes more recognizable. There will be times where that won't be allowed, mainly in some of our assessments that you will see. But what I do in examples are done so that you can see and get used to seeing these types of things. And it's important that that is done, that you see and recognize some of the ideas before you're being held extremely accountable for them. A lot of the naming that you've already done is that of monatomic ions, naming the formulas and the ions of that element. So if you just looked on the periodic table and I asked for the name for the symbol Na, you would say sodium, because that is what it is. It is the monatomic element. Now the ion version of that is if I asked for if it had a charge of the sodium plus or Na plus, that would be the ion, and that's going to happen. One important thing is that ions will never form the gain or loss of a proton. It is only the electrons that are gained or lost. The number of protons defines what an element is. I cannot stress that enough. A proton defines what an element is. A couple units ago, we talked about isotopes and the gaining or losing of neutrons. Now we're talking about the gaining or losing of electrons, and electrons only. So it is not the protons that are gained or lost. You do that, it's wrong. I'm sorry. There's no help for you if that's the case. How these look? Well, it's a little bit different. And I use a fictitious element here, BP for Palladium. It's the element that I say that a student is going to eventually find one day and name after me and give it the symbol here. Hopefully that it will ever happen. So a cation has a positive charge, and that means you have lost electrons. Now electrons have a negative charge. So this element here has lost one electron because it has a positive 1 charge. That means there's one more proton than there are electrons. An anion is a negatively charged ion formed by the gaining of electrons. Now this does not happen ever normally under normal circumstances, but finding a -7 means that you have gained 7 electrons. Not going to normally happen, I'm pretty sure about that. And so you're going to see just a negative whatever, however many it takes to gain that many electrons. Now another way to remember that is that cations are positive because cats have paws. And so you would have that as aware. Anions usually is the anti. If you were anti-homework, you would think that homework was negative, and therefore you would not want it. So when writing those formulas, it is important that we have them, and those charges are placed in a superscript. Now, I believe we do have an app, or sometimes they will have those done that way on some abilities, where you can get that positive or negative in the superscript. Sometimes you can't, and so we do take accommodations, and at least you need to make sure that the number is, depending on the device in which you're using. Main group elements, groups 1 and 2, will always form cations. Group 13 will usually also form cations. Now, if we look at our periodic table, we'll actually see the oxidation states, or the oxidation number, that they form. And that would be the positive 1 for group 1, and a positive 2 for group 2, and a positive 3 for group 13. The main group nonmetals, that would be groups 14 and especially groups 15 through 17, they will form nonmetals, and they will be based on how many they need to gain to achieve their octet. Now, nonmetals for this class only will always form anions. There are circumstances in which nonmetals can form a cation, but for this class, we will focus only nonmetals becoming anions. So how does this work? Well, when we name a main group monatomic ion or cation, all we need to do is add ion to the end of it. When we name a monatomic anion, we need to change the ending to IDE. Now, this might mean that we need to drop 2 to 4 letters are dropped and then added IDE, but it's always tough to tell and which ones work, and that's why practice helps figuring out, well, is it IDE or not IDE? Well, is it a metal or a non-metal? That's how you really tell. But how does it sound? Chloride, carbide, phosphide, sulfide, solanide, bromide, iodide, fluoride. Those are important that we hear what they sound like, so that we know, oh, okay, this is how it works, and practice spelling it outright. So let's try some out. Na is the symbol for, well, sodium. Because it has a charge, as we see here, we need to add the ion part to the end. So it's just sodium ion. Now, magnesium ion, the fact that it does not end in IDE means that it's going to have a positive charge. So the one that I'm looking at here, magnesium, symbol Mg. Now, if I look on my periodic table, I see that magnesium is in group 2. That means it's going to have a positive 2 charge. The next example, we see that we have aluminum with a positive 3 charge. That means I need to change it's aluminum, and that's it. In aluminum ion. That ion indicates to another person that I have a charge. Carbon ion. Now this one is a little bit interesting. We kind of have 2 correct answers for this. You can have carbon with the positive 4, or carbon with the positive 2. There's a different way of indicating which one is which. We'll talk about that later. Now the carbide ion, that's going to be different because it ends in IDE. Because it ends in IDE, that means the charge on the carbide, or the carbon, needs to be negative. Now O, with the negative 2 charge, Well, O is for oxygen, but because it's negative, I need to change the ending, and I need to drop, in this case, 4 letters to oxide ion. Now the nitride, now if you look on your periodic table, you're going to see that nitrogen has a number of different positive charges. Because it is a nonmetal for this class, and it ends in IDE, we're only going to talk and use the negative charge. So it's going to be N with a -3 charge. And then we have Br with a negative charge. Well, if I go on my periodic table and I go bromium, but because it has a charge, I need to change the ending to IDE. And I use the I from the previous name, bromide ion. That indicates to somebody that I'm talking about bromium that has a negative charge as the bromide ion. Now, why did we not talk about the transition metals? Well, the transition metals are a little bit different. They have a little bit other stuff going on. And when they form, they don't have this nice hard fast rule like we do for the other ones. And so if we look on our periodic table, we'll see that a lot of transition metals can form more than one ion. It is this fact that they can form more than one ion that means that we have to do this. There used to be a number of different naming systems out there. The IUPAC promotes the type of naming that we're going to go over. And we are not going to look at any great length, the alternative. So when we name transition metals, we put the element name with the charge in Roman numerals, in parentheses following the name. And then we just add ion at the end. Now I'm going to do an example of an iron ion that might not happen in nature, but it's can you understand the system and the rules that you have to follow. So for the first one, we'll look at iron 2. Second one we'll do is be iron 3. And the fourth one we do is iron 4. Now, how does that look? I say it iron 1 and iron 2, and we do probably need to have our Roman numerals, and maybe that's something that we should look at, is that 1 is the Roman numeral I, 2 is usually II. Does it have to have little brackets on the top? No, it actually doesn't. 3 would be III. 4 is IV. Not like you're sticking one in your arm. 5, you're looking at just V is for victory. 6, VI. Again, let's put the brackets there because you don't have to. It doesn't matter. 7, VII. 8 would be VIII. Oh, that doesn't look very good. And so what we have is that is how you would write them out. Not going to probably ever see a 9 or a 10, but those would be IX and X. And so those would be how we would look at it. So what does it look like when we're writing them out? Well, Fe is the symbol for iron. Because it has a positive 2 charge, I say 2, but I write the Roman numeral 2 and have ion. When I look at iron 3, again, Fe is for iron. I say 3, however, when I put it inside parentheses, I use the Roman numeral 3 with ion following the outside. And for iron 4, this is the one that most likely is not going to happen, but do you understand the system? And that we would use is Fe is for iron and the Roman numeral 4. I do use some elements as in examples so that you, and in our assessments, that don't happen for the simple purpose that you can't Google the answers. Ha! Now, this is known as stock or Roman numeral naming system and is promoted by the IUPAC. The old system used endings such as IC and OUS, and that's kind of where you would have the coop, Rick, Ferris. We had the +3 charge. It was iron with the +3. Not the easiest way to always remember. There's some people that love this method. I was never a big fan of it. It is not promoted by the IUPAC, and therefore you don't have to worry about it. But do know that it is out there. So, how do we do this naming? Well, here we go. CR, find it on your periodic table, and you're going to find that it is chromium 3 ion. Why 3? Well, because there's a 3 written right there. Vanadium is for V, so writing's bad. Vanadium 5. Now I don't write the number 5, I write the Roman numeral 5. Ion. Now the next two are ones that really bother me. And this mainly because a lot of people fail to write the Roman numerals when we write them out. And I have a problem with this because a lot of students aren't going to know, for the most part, that silver always has, for the most part, a +1 charge. So you'll see this both back and forth, and it's to kind of get you used to understanding that some of these, we don't say the Roman numerals if they only form 1 charge the majority of the time, such as silver 1 ion. You might just see it as the silver ion and have to know that it says silver 1 ion. How are you supposed to know that? I don't know unless you've been taught. And a lot of times they forget to tell you that, oh, look, this is one of those ones that always forms this. Silver and zinc tend to be the two ones that do that as well. So for zinc, use Zn, and because it has a 2, +2. But if you didn't know that, and you just were looking at a periodic table that didn't have that written in, how are you supposed to know that it's that way without being told? Now this Roman numeral naming system can also be used for other metals that form positive charges, such as tin and lead. We will use those in those cases. Now, the hydrogen ion gets to be a little bit interesting. And it's when we look at it when it forms what's called the hydronium ion. And that's when it just has 1 proton. It's basically all it is the hydronium ion. It is extremely reactive because all you're dealing with is just that 1 positive proton. It's extremely reactive. And what it is, it does have a name. It does form the H3O plus ion, and that's kind of where it's the hydronium ion is kind of looking at the concentration of that. Leads us to understand how acidic an item might be. Something that we might want to look at, but it is there. So, polyatomic ions. You're going to want to flip your periodic table over, and you'll see a good number of polyatomic ions that you should be able to recall from memory, or at least look on the back of your periodic table of them. are named as they are written out on that sheet of paper. They involve in ionic compounds, solid, crystalline, or amorphous. You are responsible for knowing these ones. The only polyatomic ion that is a positive that we'll deal with is the ammonium ion, which has the hydronium ion attached to it. It's ammonia with the hydronium ion. Ammonia, not ammonium. But as you'll see, there is a pattern to those when it becomes naming. So it is important that you pay attention to those naming of ions. Now in the next unit, we'll look at combining these ions and putting them into actual compounds.